Hello, my name is Denali. I read the Probabilistic tiny recursive model paper, and so without further ado, let's get into it. So two things I'm going to define. Latent space, that is a vector that encodes things internally that the model has, like it represents something, and then deterministic. So a deterministic algorithm takes one input to one output. A non-deterministic algorithm is random, so you get one input and you can get multiple outputs out of that. So reasoning is very important. Reasoning is the repetitive refinement of a solution. So define, challenge, edit, repeat, as Socrates put it. Probably not that same word, but so a quick note. So LLMs do chain of thought reasoning. They have internal reasoning circuits, but neither of these are great. So tiny recursive models are built from the ground up to reason. And here's a visualization of a tiny recursive model moving like an answer latent through space. So what it kind of looks like is that there's a loss landscape, and the tiny recursive model can move the answer latent to an area of lower incorrectness. So here is prediction minus our actual answer for a math problem. I like the multiplication division because it's more complicated and you get kind of weirder traversals. Here it's getting very, very wrong, and then it goes back to being right. You can play around with it in the notebook. So what does this look like? Transformer, input, multiple unique transformer blocks, you get an output. With a tiny recursive model, you have your input, you have a latent reasoning vector and a latent answer vector, and so these are actually fixed in initialization of the paper. So it's random, but for every single example it's the same. We'll talk about that more later. Then you have your transformer blocks, usually it's 2 to 4, and you update your reasoning latent number of times, then you update your answer latent once, and you go back and you do that cycle a certain number of times. The LM head takes your answer latent and decodes that into the puzzle, and the Q head basically looks at the answer latent and guesses whether it's correct. So what does this look like in code? It's kind of cool to note that we don't actually do the computation graph over the entire recursion because that would explode. So what we do is only for the last answer update step do we take a computation graph, and that is actually sufficient to train a model. We don't actually have to do the computation of the entire thing. And important to note, the Q head is actually used to allocate like training to harder problems. So if it's an easier problem, we don't actually have to train on it the entire time. If the Q head is greater than 0, we just stop because it's solved. And that's just kind of cool. It's called adaptive computation time in the paper. And then here's inference. So we also repeat this a certain number of times, the number of superposition steps, and we get an answer. So you may be saying, cool, this is cool, but does it actually work? This is state-of-the-art LLMs for when the paper was out, and we can see we're order of magnitude less parameters, but we actually do problems that LLMs just can't do. Like they get 0% on Sudoku, but we can get up to 80%. And so this is great, but also has some pitfalls. Because it's the TRM is completely deterministic, one input gets one output. So if it's wrong in a puzzle, we can't really fix that. So how do we fix that? Well, the actual problem is that in this latent answer space, there are local minima that our models get stuck in. And so you could see it got all the way to one cell being incorrect, but then it kind of just backtracked because it couldn't really find a path to the correct answer. And what we can do is that to get out of local minima, we can just add noise. And what's great about that is that it's very simple. It's one line of code. We just add noise to latent reasoning. And we don't have to return the weights because we don't mess with the weights at all. But also because it's non-deterministic, we can have we can run this as many times as we want and get individual answers. And this is the number of rollouts. So here we can visualize that. We have a Sudoku problem. It's the same Sudoku problem as before, but we just run a bunch of rollouts that are probabilistic. And as you can see, they converge to this value. And when we have all these rollouts, how do we score it? We actually can use the Q head because it's trained to predict whether it's correct. It actually is pretty good at separating correct rollouts versus incorrect rollouts. And so how does this scale? Just go over this quickly. Pretty logarithmically for most things. The number of times we refine the latent, the number of times we reasoning and answer, the number of times or number of rollouts we actually have. So that's pretty nice. We can just throw a computer at the problem, which is always great. But the number of layers and the size of the dimension actually don't scale logarithmically because the problem with Sudoku is not the amount of information you store, it's actually the amount of reasoning you can do. So it's not always great. So why just add noise? This is something that came through my head. It's like, why are we just adding noise at every single step? Because what if we're correct and we're throwing off the reasoning? So we can actually exit that the correct minima. So I tried a few things. I tried smoothing the noise with momentum. I tried randomized starts. This was kind of interesting. Of like, okay, why does the paper only have a fixed position where everything starts? Why not just perturb it a bit? And then inertia. So it's a tiny recursive model, but it has inertia to try to get out of those local minima. And you can see that inertia failed. Oops. And that randomly initializing is actually a lot better than like a PTRM, which is kind of surprising. Here's a graph, a chart run on 128 medium difficulty Sudoku problems, and we actually get a 10% increase in performance over a PTRM by randomly initializing our starting positions instead of adding noise at every single step. So that was kind of cool. And that was an extension I made. And then I was also confused on the Q head because it predicts whether we're correct, but it's a linear layer, so it doesn't actually have that much compute. So what's cool about it is because it's in the loss, it's actually forcing the model to store the correctness of like how correct it thinks the answer is in the latent answer, right? And so just to show how this works, because it's a linear layer, we can just add that to our current answer latent, and we can get a new latent, and we can decode that. And if we add the Q head to our latent, we get the model predicts that it's a lot more confident in the Sudoku problem it's outputting, but the correctness doesn't change at all. It just kind of, is noisy. So this is called what I call a sophist. It thinks it's more correct, but it actually has made no progress at all. And so I made a sophist model. It's very similar to one of the things they tried in the paper. But if we, at every time we update the latent answer, why don't we take the derivative of the Q value with respect to our answer latent and then just take a step. And doing that, we actually don't get an increase in performance because we're increasing the Q value, but not actually the information in our answer. And so we get pretty much the same performance as a regular tiny recursive model. But what I noticed is that we actually don't increase the Q value that much, which is kind of interesting, but also for incorrect answers. It's even more apparent that we don't increase the Q value at all. So what I'm thinking is that the model internally understands when a Q value is too high and can compensate for that, which I just find pretty cool. And then some takeaways I have, I really like making this project. I hope you enjoyed and learned something. Adding noise to reasoning process is always beneficial. If you can go outside and go talk to birds, that will help you with your reasoning. Non-deterministic outputs always allow you to throw compute at the problem if you have a good Q head or scoring function, but the reverse is not true. So we can't optimize based on the scoring function. And also, never get Fable5 to play Sudoku. You will run out of your usage for Cloud Code very fast. So.